Let's look at arc lengths for polar curves. We'll actually look at three views of it. One view, let's say we have this point here and that point here, and we want to say what's the length of that curve between them, kind of all in one shot. Like this is just a small slice of a larger curve that we're doing. You could say, well, if I know the location of this point and the location of that point, I could say, let's draw a right triangle, kind of like that. Make it easier to see. And this distance, we'll call that dx, because that's how much x changes from this point to that point. At least you could call it delta x, but we're imagining that it's really small. And this distance, we'll call that dy. And then what's the distance from this point to that point? That would be kind of the distance along the hypotenuse there. So we could say that that hypotenuse distance is what involving dx and dy? We'd probably say dx squared plus dy squared, just the ordinary Pythagorean theorem. And then the question is, well, what is dx and what is dy? Well, we could say x at time t, or location theta, is equal to r of t times cosine t, and y of t is, do you remember, r of t times sine t. So we're basically saying let's use parametric ideas here. So we're saying t is the same as theta. So that gives us x and y, and then we could get dx and dy by doing x prime and y prime. So we could say x prime of t equals the derivative of that. That's going to involve the product rule. Same thing with y prime. So it's a lot of by-hand calculus, not very fun. And then we have to do some algebra, and then we do some more algebra. And then what you get is that that distance is the square root of r squared plus r prime squared times d theta, which itself is not a bad formula, right? It certainly has a Pythagorean feel to it. It's a little weird because r is usually in different units than r squared, or r prime, so it's not exactly clear why that would all work out, but we can talk about that later. So that's the area, that's the arc length of one little segment like that, and then we would just integrate that from the theta starting point to the theta stopping point. So that's one way to see it. Let's take it another view. And this one avoids the algebra and links back to some stuff we learned in Calc 1. So let's look back at Calc 1. If you had x here and x plus dx there, and you had some function and it was increasing at some rate, and this is y, and this is y plus dy, you might say, what's its value of up here going to be? And you might say that f of x plus dx is basically f of x plus the slope times the horizontal distance. Slope times dx. This is basically the tangent line formula, right? And now, now that we're in Calc 2 and we've seen Taylor series, we know that that's actually a first-order Taylor approximation. So it's some good linking concepts there. And this slope, we could call that f prime, right? So we're saying if I'm here, I can predict how much change I have in y by taking the slope and multiplying it by how far I'm moving in x. So now we're going to do that in polar coordinates. Let's redraw this idea. So we'll have something like this and something like this. And we've got a curve going from one spot to the other. So Same basic diagram that we're starting with as up there. But now instead of thinking about a right triangle here and there in the x direction, let's think about if the radius hadn't changed at all, then we would have moved over here. And since this is a radial, this is part of a circle, we could say a straight line circle. It's not going to matter too much as long as it's small. But it's going to be basically at a right angle to a ray coming up from the origin. Let's call this length A and this length B. What can we say about A and B and then the length of the line connecting them? So let's talk about that. So what's the length of A? Well, it seems like it would be d theta, but it's d theta out at a particular radius. The larger the radius, the larger the length of that little segment. So it's actually r times d theta. How about B? Well, using this idea, B is the increment from here to there, which is like the y increment there. So it's r prime at theta times d theta, just like here we had f prime times dx. And then what's the length of that hypotenuse? It would be the square root of a squared plus b squared, which is the square root of r d theta squared plus r prime d theta squared. And we can do the squaring on each part, so we get r squared d theta squared plus r prime squared d theta squared. And we can factor out the common factor of d theta squared, and we get square root of r squared plus r prime squared times d theta, which is basically the same thing we got there. So two different views, thinking about the right triangles going on in two different ways, but we end up with the same formula, so that's good. And then the total arc length, will be the integral from theta equals some starting value to theta equals some stopping value, square root r squared plus r prime squared d theta. Seems like a straightforward integral to write. The problem is, like a lot of our arc length stuff, you're ending up with squares inside a square root. The integrals are really, really hard to do in all but the simplest of cases. So it's okay with me if after you formulate the integral, you go ask Wolfram Alpha to compute it, unless it's really, really simple. So it's doing the antiderivative that's the hard part. And in our next video, we'll take a spreadsheet look at this whole thing and think about yet another view of thinking about arc length.